All right, there we go. So we'll be covering consumer preferences and budget constraints as well. So just in terms of what we will be going over more specifically, we'll start with preferences. We'll be looking at the assumptions that go into what we know as preferences or realize as preferences in economics, as well as the symbols that we use to describe preferences. After that, we will be covering indifference curves, what the normal curve looks like, perfect substitutes, all those special relationships, perfect complements, quasi-linear function curve, as well as the Cobb-Douglas function curve, which is probably going to be the most common thing that you will see just because it's the quote-unquote perfect economic function curve. We'll also be going over some marginal rate of substitution, as well as budget constraints, covering the budget line, changes in income, price, and what happens to the budget line if you see a change in both income and price. So we're going to start with preferences, where we focus on the consumer's choice among affordable bundles of goods. Given that these preferences and the consumer is rational and well-behaved, they can rank all of their bundles in order in terms of what the goods actually are. And the consumer set of affordable bundles of goods depends on prices and on their income, which is a reference to what we were going to see in the budget line at the end of this presentation. The underlying assumption is that consumers can rank bundles according to their preferences. Different individuals have different preferences, but there are certain properties or preference rankings that can apply to most individuals. So let's just say take any random individual, and let S be a set of consumption bundles. Assume that the individual can rank all bundles of goods within that set that we're going to refer to as S from now on. And the symbol used to denote their preference relation is the one at your bottom right there. We use that to say weakly preferred or weakly better good. So the good on the left of that would be the weakly better good to the good on the right of that. That means at least as good, by the way, but I'm sure you've covered that. So if we look at S as a set of two goods, both goods being perfectly divisible, sometimes you'll see goods in economics that are not perfectly divisible. When they say something like that, they're typically talking about a manufactured good. For example, you wouldn't go out and buy half of a car, 0.1 of a car. But typically in economics, when we talk about commodities, in this case, we're using cheese, we can talk about perfectly divisible goods, in which case the graph just looks a lot nicer. So we'll make mathematical statements about preferences using symbols. The one that you see on the bottom to your left there is again weakly preferred. The middle is strictly preferred, and the one on the right would just be your indifference symbol. So again, we just discussed this a little bit. The first line would mean that X is weakly better than or weakly preferred to Y, and the symbol to denote indifference is the middle one. So if we strictly prefer X to Y, you have that symbol, and it only occurs if and only if X is both weakly preferred to Y and Y is not weakly preferred to X. So in terms of the assumptions we're making, and I assume you can let me know if we got people waiting in the waiting room. Let me know if I mention anything that you have not covered, just because I will not go into that axiom of preferences in depth, but I'm going to assume that you covered the same stuff that I did. So the first thing that we're going to be looking at would be your completeness preference. This is basically just saying that given any two bundles, X and Y, the consumer can rank them. Some of these are going to be more obvious than other ones, and then we'll get to things like continuity, which is very hard to contradict. And quite frankly, I'll tell you exactly what my prof told me about continuity is not really something that you need to worry about. We also have transitivity. So if we have goods X, Y, and Z, good X is weakly preferred to good Y is weakly preferred to good Z, and good X is weakly preferred to good Z, then good X must be weakly preferred to Z. So if you have apples, oranges, and pears, and you prefer apples to oranges and you prefer oranges to pears, it wouldn't make any sense to say that you prefer apples to pears, or then you must prefer apples to pears. It wouldn't make any sense to contradict that. Within monotonicity, we have three types. So we're going to be looking at weak monotonicity, regular, and strong. In general, monotonicity just says that if bundle X has more of both goods than bundle Y, then the consumer strictly prefers good X to good Y. If you want to sum this up in a sentence, it's basically just saying that more of a good is always strictly preferred to less of a good. Within that, we have the subsection weak monotonicity, and the statement there is just that more never hurts. More is at least as good, and the indifference curve for weak monotonicity is never upward sloping. For regular monotonicity, we just say that more of everything is strictly better. That's what we're talking about here on the presentation. And the indifference curve is never upward sloping or thick, but it is okay for it to be horizontal and linear. Whereas if we look at strong monotonicity, we said that more of something is strictly better than all others that have been at least the same, and your indifference curve is always downward sloping. We're also going to be talking about continuity, and this is basically just saying that if you have a series of goods, it's going to converge eventually as your exponent goes to infinity. It's not really something that you need to focus on at all. In fact, it doesn't come up in the course at all, at least from what I've seen, and I took D1 and D2 at this point. Jake. Beyond that, we're also going to be talking about something called convexity. So if someone in the group chat could just let me know if you have discussed convexity, that would be great. But it basically says for regular convexity, when you take the average of two bundles while you're looking at your indifference curve, that this average of the two bundles is at least as good or weakly preferred to the reference points. We'll go over that a little bit more in a second. And the indifference curve, if you have regular convexity, your indifference curve slope is always going to be negative, and it's also always going to be increasing and linear, or it can also be linear. Whereas if you have strong convexity, same concepts apply, but it cannot be linear. So now we're going to move on to the next section, being indifference curves. So if we have an indifference curve in terms of good X, it's going to be the set of bundles that are as desirable as X. So if X is a reference bundle that you have, all of your points on the indifference curve are going to be just as desirable. You're, as a consumer, are going to be indifferent between all of these different bundles. Do the assumptions that we made in the last slide. The indifference curve, or the indifference set, must be a curve that passes through X. So we'll use this throughout the rest of the presentation just because indifference set and indifference curves are interchangeable terms. An individual's indifference map is the set of all indifference curves that represent their preference rankings. So an indifference map will contain all of the different levels of utility for the consumer. And then the properties of an indifference map include just that the indifference curves cannot cross each other, because if you have multiple indifference curves crossing each other, that just means that theoretically, obviously it can never occur, but theoretically both of these indifference curves would also be indifferent to each other. Then you have to worry about it having some length, just because once you have these indifference curves, you theoretically be able to move one curve along the other one. It would just become everything being indifferent to each other. We're also going to make the assumption that indifference curves always slope downwards and indifference curves are not thick. So here's an example of an indifference curve for the consumer, where we've got some bundles up there, W, X, and Z. If you look at that, your indifference curve I, bundles X, Y prime, and Y double prime are all indifferent to each other. Whereas all three of those that are indifferent to each other are strictly preferred to bundle W, and bundle Z is strictly Bundle Z is strictly preferred to the rest of the bundles on the screen right there. The issue being typically that if this is your optimal choice for a consumer, your bundle Z will not be affordable. It will be outside of the range that they can focus. It will be outside of the range that they would be able to purchase given their consumer preferences in terms of their budget and the price of the goods. So the consumer is indifferent between X and Y. Bundle Z is strictly preferred to X. Bundle W is strictly preferred to Y. And you will have your formula on the next slide, I believe, for your indifference curve. We're going to go over some of the special cases, quote unquote, when it comes to indifference curves. The first being perfect substitutes. For example, in this case, we have Californian oranges and South African oranges. I do not know if there's a difference between these two. I'm going to assume that there's not, because that would back up the example, but we are going to make the assumption that these oranges taste exactly the same. So the consumer does not care depending on which type of orange they get. Your utility function down there, and these are things that you should memorize, whether it be perfect substitutes, perfect complements, or whatever type of other goods or phenomena you will see in economics. You should probably have these memorized going into the exam. Fortunately, they are very self-explanatory. Another example of this one would be if you have a blue pen versus a black pen. As a user, you don't care which one you get. So as long as the price on one of them is better than the price of the other, we're going to choose the cheaper item. Next, we have perfect complements. So point A represents at least one pair of shoes, while point B represents 2 pairs of shoes, and point C represents 3. Now, this is the typical case for perfect complements, right? Because if we have 1 left shoe and 10 right shoes, we only have 1 pair of shoes. So it doesn't really make a difference. We can throw out 9 of those right shoes. We don't care. Your utility function is going to be denoted utility equals the minimum of X1, good 1, and good 2. So your utility is always going to be, for example, if you have 1 of good X1 and you have infinity, if you have a million right choose good X2, your utility is always going to be 1, right? Because you don't have a use for the rest of those. This was an interesting one as well, because the graph you can see there, it does not look like, it looks distinctly different than any of the other graphs you will see in economics. So this is an important one. Professors love to give this on exams just because of how odd it can be. And at the same time, it's important to realize that it does not always have to be a 1-to-1 ratio for complementary. So let's say you have an individual who only likes coffee with 2 packets of sugar in it. You'll see a question where the professor talks about how you need 2 packets of sugar for every 1 cup of coffee, which changes the graph up than it is here because this is a 1-to-1 ratio. So the ratio is where you'll trip up there and what you have to pay attention to. We're also going to have quasi-linear utility functions. So basically your utility function there is just going to be f of good 1 plus good 2, where good 2 is measured on the vertical axis as usual, and good 1 is measured on the horizontal. We're going to make the assumption that the derivative with respect to x1 is greater than 0 and the second derivative of x1 is less. So what that means is our slope is always going to be downward sloping, and at the same time, our indifference curve is always going to be concave upwards. And this is probably one of the most important things when it comes to D1. If you're going to have something that you really need to know for the exam, just have this down dead to rights. This is something that's guaranteed to come up. You're probably going to get 2 to 3 questions involving your marginal rate of substitution. I know in this second semester, Professor Duda will probably refer to it as your technical rate of substitution or technical marginal rate of substitution, although it's the same exact thing. What you're looking at there is that your marginal rate of substitution between these two goods is going to be equal to your partial derivative of your utility function with respect to good 1 over your partial derivative of the utility function with respect to good 2. If you've talked about marginal utility already, you can break that down into a smaller part, which is how I like to do it personally. So that would just be your negative marginal utility of good 1 divided by your marginal utility of good 2. This is just conceptually saying that people are willing to give up a bit of something in return for a bit of something else. So if we consider an indifference curve that passes through X, through a certain bundle, the slope of the curve at X, at bundle X, is a measure of how many additional units of good 2 an individual is willing to give up in exchange for having an additional unit of good 1. And if she was to do this, she was to give up good 2 for good 1, we would have a constant utility at that level. And our marginal rate of substitution for good 1 and good 2 at the point, or at the point of bundle X, is just the ratio of marginal utilities at that point. So next we're going to be talking about budget constraints, but I would like to touch on Cobb-Douglas preferences very quickly. So for Cobb-Douglas preferences, I'll make an addition to this before I send out the notes to you. I'm going to make some changes. It's just the utility of good 1 to power alpha times the utility of good 2 times power beta. This is just a parabola that really embodies well-behaved consumer preferences. It's the stereotypical monotonic curves. You're probably going to see this just because it works out so well. You're probably going to get one of those on the exam, as well as something else that is a little bit more oddly behaved. So that would be one of the special cases. So now we will continue to budget constraints, which is probably the first thing that you all covered. Is it's one of the easier things. It's literally just slope-intercept form. For anyone who took math in high school, you're going to be able to handle the budget constraint. So if you're given the prices for good 1 and good 2, price 1 and price 2, and a budget Y, which your professor probably denotes as M, the budget constraint is going to be the price of good 1 times the quantity of good 1 plus the price of good 2 times the quantity of good 2 equals your budget. So if you want to rewrite that, you can do the quantity of good 2 is equal to your budget minus the price of good 1 times the quantity of good 1 divided by the price of good 2. The slope of this line is always going to be the slope of the line if you were to graph it, so that would be negative price of 1 divided by price of 2. And for example, if you have the slope price 1 divided by price 2 equals 1/2, that would indicate that selling one good or 1 unit of good 1, then the consumer can buy half a unit of good 2. So this is also referred to as the marginal rate of transformation, basically the ratio that we can transform good 1 into good 2. And you'll get a lot of questions that are similar to this, especially since you do have practice sets, but I'm sure you've already covered that. This is going to be used on the exam in combination with utility just when it comes to determining your optimal bundle set. Have you all covered determining your optimal bundle set yet? Where your utility function intersects or isn't tangent to your budget constraint? Or is that something you haven't been over yet? All right, great. Because you're going to get at least 2 questions on your midterm exam about that. And then as you go on to the second semester, because they are cumulative, it's important to still understand it. Yep. So here's an example of it. If we have Jose's budget line, Jose likes to collect t-shirts and movies. The number of t-shirts he's willing to buy is on the x-axis, while the number of movies he's willing to buy is on the y-axis. His budget constraint is $56. A t-shirt costs 15 and movies, or 14, and movies cost $7. If he spends all of his money on t-shirts, he can only buy 4 of them. So that's how we get our y-intersect there, our horizontal intersect. And if he spends all of his money on t-shirts, then he would be able to get 8 of them. So that's how we get that. And these budget lines are always going to be linear. So if you need to graph it on the exam, you can literally just do those 2 simple equations, graph it, draw the line between them, and you're good to go in terms of a budget line. So here's another example. We have the same exact graph, except you need to understand that his not feasible purchases, the purchases that are too expensive for him, are on the outside of this line, while the feasible purchases are all on the inside. The difference being that all the possible optimal bundles are on his budget line right there. So although he can purchase everything in here by the not optimal feasible section, he would not want to do that, assuming that he is a well-behaved and rational consumer. So we'll look at it again. Specifically, if you have a change in income, a change of income is just going to inspire a shift inwards of your budget line. So assuming you literally just have a change in your income and not a change in price as well, it's just going to be an inward shift. Increase in income, it's going to be an outward shift. So if Jose's budget drops from $56 to $42, the budget line will shift inwards, so he's unable to purchase the same number of goods as before. If he plots the new budget line, he can find the intercepts as before and connect them, so it's the same exact process. And there will be fewer opportunities for consumption as well. The alternative change would be a change in price. So this is just going to be a rotation of your line about the point. So let's say the price of movies is changing. It's going to be a rotation of the line about the price of t-shirts, or the horizontal intercept, and vice versa as well. But the main difference between these two is that a change in income will not change your slope, but it will change the intercepts, whereas a change in price will change your slope, but it's going to leave one of your intercepts the same. So if movies double in price from $7 to $14, of course, you can only purchase half as many, and the line will shift as well. Find the intercepts. So if you were to go about doing that, it would come out to be 4 and 4, simply because the prices of now t-shirts and movies are the same. And again, he has fewer opportunities for consumption. So a lot of the times you'll see a case on the exam or on your midterm where the professor will outline a change in income and price. So what you need to realize here is that it's probably not to try to conduct this visually. You're going to have to come back and just redo the calculations, but thankfully it's the same exact process. Again, you're just dividing, plotting the intercepts and drawing a line between them, so it's no big deal. So for example, if we have the price of movies increase from $7 to $12 and Jose budget increases to $63, then the y-intercept will fall to 5.25 and the x-intercept will fall to 4.5, excuse me. And it's okay to have decimals here as long as your prof has not outlined otherwise, simply because we're always going to assume that our goods are infinitely divisible. So here's an example. I'm sure you've seen this already as well, but it's very important to have this down. Formulas are very simple and you can derive it very quickly on the exam as well. However, in my experience, you're probably going to be tight on time. So if you don't have these things memorized, it might be a good idea just to skim them over right before you walk into the exam room and be good to go. So the slope, well, we'll start with the intercepts. The intercept is of course going to be your total budget divided by the price for each respective good. And in addition, the formula for the line is going to be your quantity of good 2 equals your budget minus your price of good 1 times your quantity of good 1 divided by your price of good 2. I like to organize it in slope intercept form. That's what I was used to in high school. But if you like to do it in, I don't even remember what the alternatives were. If you like to do it with some sort of alternative linear formula, go for it. It doesn't make any difference. But in the end, if you want to derive it, you're going to be starting with the your total budget equals the price of each good times the quantity of each good plus the price of the other good times the quantity of the other good. So for this example, suppose that the price of good 1 is 3, the price of good 2 is 6. Then our slope is going to be 1/2 just because we're dividing the price of good 1 divided by the price of good 2. So if we start at point A, if the consumer reduces her consumption of good 1 by 1 unit, she can increase her consumption of good 2 by 1/2 unit. And here again, our marginal rate of substitution or marginal rate of transformation, of good 1 into good 2 is going to be negative 1/2. So that's the end for today. It was a very short one today. In the future, we will be covering a lot more. However, if you have any questions, feel free to reach out to our email or our Facebook. You can reach out to our honors rep, Matthew, on Facebook. Alternatively, you can reach out to me I'm on Facebook, LinkedIn, Instagram, whatever you want. Just shoot me a text. I'm also in the group chat, so if anyone has any questions there, I'm sure I can help. So yeah. Thank you all for coming. I'll get this video uploaded to YouTube. If you have any questions, feel free to ask right now. Otherwise, you all have a nice day. The difference between a curve and a line in terms of economics. So obviously your curve is going to be, I wish there was a better way to say this, but your curve is going to be nonlinear. But in terms of a difference, there really is no difference. In both cases, it's just going to include either a bunch of sets that we can consume or that have the highest level of utility given our budget. But typically you're going to see a curve with utility and you're going to see a line with your consumer constraints. So if I was going to do it myself, if I had to group them, I would just say that if I see a curve, I would assume utility. And if I see a line, I'm going to assume constraints. This isn't perfect, of course, because you do see with, I'll go back to it right now, some of these special cases. So if you have perfect complements or perfect substitutes, it is going to be a line. But seeing as you're going to be the one who should be able to recognize that it is a case with perfect substitutes or perfect complements, you would be able to discern. So I would probably go into the exam. If I was going to do something, I would like dash my indifference curve, and then I would just use a straight line for my budget line. Regardless, neither of these are going to be thick lines or thick curves. So there's only going to be one set per each like infinitely small unit. All right, if that's it, I'm going to end the meeting and I will get this posted to YouTube. I'll see you guys in the next one.